Good morning. Hope everybody's doing all right this morning. So we are going to move on to chapter 4 this morning. So this is 4.1. I did open up just before class the content folder for chapter 4. So if you're looking for those slides, they should be available now. Let me know if you still don't see them. Um, so before we do that, though, just a couple of reminders. Don't forget the test for chapter 3 was posted at midnight last night. That means you've got until Wednesday night, tomorrow night at midnight to complete that. So again, just make sure you find some time either today or tomorrow to sit down and take that test. The other thing that's due by midnight tonight is the 3.7 and 3.9 homework. So if you haven't finished that homework yet, just make sure you get that done. And then the 4.1 to 4.3 homework right now is scheduled for Thursday. We'll see how far we get in the next couple of days. I might push that back to at least Friday, depending on how far we get today and tomorrow. So just know that this is one of those homeworks that you're probably better off waiting until we get through like section 4.2 and really 4.3. Just because it'll really shorten the process for how you do some of those problems. You still need to know how to do the process from 4.1, but we'll get to shortcuts in 4.3. So that's why I say, probably do a few of the problems early just to make sure you know how to do this process because you will be asked to do it on the test. But most of the problems on the test will be involved with the shortcut. So I would say, once we get to 4.3, you'll be able to do those problems a lot faster. Okay. Think that's all I've got right now in terms of announcements. So any questions, comments, or concerns about anything before we get started? All right. So like I said, this is 4.1. We're going to look at the long way to do these problems first, just to gain an understanding of what we're actually doing. And then, like I said, by the time we get to 4.3, then we'll have those shortcuts similar to what we did back in chapter 3, right? We have the limit definition of a derivative, and then we actually got to the shortcuts to find those derivatives. Same thing here, okay? All right, so areas and distances. So the first thing we want to do here is use rectangles to estimate the area under this parabola from 0 to 1. Okay, and so you can see they've given us the parabola here. They've given us the interval from 0 to 1. We're trying to get an approximation for that area S. Okay, that blue shaded region is what we're trying to find. Now, it tells us we're going to use rectangles to do that. Okay, so in this case, I'm going to tell you how many rectangles we want to use. It'll be the same case in the homework. They'll tell you how many rectangles to use to approximate. So we want to use 4 rectangles. So I'm going to let that be my N value for this one. Okay. Right, give me 1 second. My pen's not writing. All right, sorry, I'm having to restart that device. It was working earlier. For some reason, it's not now. So give me 1 second. All right, so I think we're back up and running now. All right, so we want to use 4 rectangles here. So again, I'm going to let that be the n value. So whenever you see an n value on problems like this, that's telling you the number of rectangles you want to use for your approximation. So what we need to do now is we're going to subdivide this interval from 0 to 1 into 4 rectangles. Well, if I do that, where's that first rectangle going to land then? If I'm going from 0 to 1 and I need 4 rectangles, where am I going to stop my first rectangle here? In other words, how wide would the rectangle need to be? So let's think about it this way. I'm taking my interval from 0 to 1 here. I'm going to divide it into 4 equal pieces, right? So I'm going to cut it in half here. I'll take half of that there, and half of that there, right? So now I end up with 4 intervals here. So how wide is each one of those pieces? So if I take the interval from 0 to 1 and I divide it into 4 equal pieces, what would the width of each of those pieces be? 1/4, right? Okay, so each one of these is going to be 1/4. So now we just need to figure out where are these going to land. So I know the first one is going to be right here at 1/4. The next tick mark then would be what? If the width is 1/4. 1/2, good. And then the next one would be where? 3/4, perfect. Okay, so that's the first step here, is just to figure out, okay, I've got my interval. I need to know the width of each. So you're taking the length of that total interval and dividing it into the number of rectangles that you want, which in this case is 4. So we're just doing 1 divided by 4. That gives us 1/4. So each one of those rectangles is going to be 1/4 wide. Any questions about that step? All right, now, if we're looking for an area for a rectangle, what do we need to know? How do we calculate area for a rectangle? Length times width, right? So those are the 2 dimensions we need. Well, we know the width of each of these rectangles, right? That's going to be 1/4. So now we just need to find a length. Well, what we're going to do then, I'm going to follow this up to my curve here, and I'm going to draw a rectangle at 1/4. And then I'm going to do the same thing at 1/2. I'm going to follow that up to my curve. I'm going to draw a rectangle like this. Do the same thing at 3/4. I'm going to draw a rectangle. And then finally, we have the one right here at 1. There's my last rectangle. Now, if I want to know the areas of those, I need a width and I need a length. Well, we know the width is 1/4. How would I find the length? Let's talk about this first rectangle from 0 to 1/4. How would I find the length or the height of that rectangle now? All right, good. We need to know what is this y value over here, right? Because that would tell us the height of the rectangle. Well, how could I find that y value? Good. We know the x value. We know the function, right? Y equals x squared. So we can just take that x value, plug it into our function, and that'll tell us the corresponding y value, which should be the height. So I'm going to calculate f of 1/4, plug that in for x. So that's 1/4 squared. And so what's the height of that rectangle going to be? Good. 1/16. So 1/16, that's the height of our first rectangle there. Now we need the heights of our other three. Okay, so next I'm going to plug in what? 1/2. Good. So that's our next value. And that's why I said we have to find these values on the x-axis first, because those are the values we're plugging in to get the heights of these rectangles. Again, I'm plugging that into my function. So this is going to be 1/2 squared. What's that going to give us? 1/4. Good. The height of the next rectangle, we're going to plug in what? 3/4. Good. And what is 3/4 squared? 9/16. Perfect. And then finally, we need f of what? 1. And 1 squared should give us 1, right? And they give us that point, right? 1, 1 is a point on that parabola. All right, so now we know the heights. So now if I want to know the area, what are we going to do next? Okay, good. Multiply length times width, right? So let's start with this first rectangle. What's the width of that first rectangle? 1/4, right? And the length we calculated is 1/16. So we're going to have 1/16 times 1/4. That's the area of the first rectangle. Now we need the area of the next rectangle, and we're just going to add it so we can add all these rectangles together. What's the length of the next rectangle? And what's the width of the next rectangle? Be careful, right? The x value there is 1/2. What's the width of that rectangle, though? Still 1/4, right? All of these should have the same width. This is still just going to be 1/4 times 1/4. All right. What about the length of the next rectangle? 9/16. Good. Width of that rectangle is still 1/4. Perfect. Plus, and then we have 1. Sorry, I'm squeezing this in down here. And it's going to be times 1/4. See if I can make that a little clearer. Okay. All right, so again, the widths here should all be the same because we divided that evenly along the x-axis, and then we just have to know the heights. Now, because all the widths are the same, that's actually a common factor between these. So another way to do this is just to take the width, which is 1/4, and then multiply it by the sum of all the heights. So 1/16 plus 1/4 plus 9/16 plus 1. Okay, and so that's the way we're going to actually do it from here on out, right? Once we know the width, we can just put that out front, and then we can just add together all the heights, and that'll give us the same thing as just finding each area individually and adding them all together. All right, so let's do that calculation now. So if we put that in the calculator, what's that going to give us for our area? The decimal or a fraction is fine here. All right, good. So 15/32. Or if you prefer the decimal, it's 0.46875. Okay, so again, either one of those answers is perfectly fine. Now, again, this is just an estimate of the area under that curve. Is our estimate an over approximation or an under approximation for the actual area in that shaded region? Think about the picture that we've got here. Do you think the answer that we got there is going to be too high or too low in terms of the actual area in the blue shaded region? It's too high, right? Because if you look, I've got all this extra space up here that I'm calculating that's not actually part of that blue shaded region, right? Okay, so this is actually an over approximation of the actual area. Because all my rectangles are actually outside of the curve this time. I'm calculating all the blue area, but I'm also calculating some stuff that shouldn't be part of that, right? Okay, so 0.46875 or 1530 seconds is an over approximation. Any questions about that? Okay, now I want to redo this same problem with 4 rectangles still, but I want to get an under approximation instead. And then that way I'll kind of have an idea of the range of values that my area could be. So what do you think we might be able to do here if I want to get an under approximation instead, but still use 4 rectangles? Tell me this, where would the rectangles need to be if I need an under approximation instead? They need to all be under that blue line, exactly, right? They need to be inside the curve, because right now I've got some that are sticking out of the curve and we're getting an over approximation. If I can get them all inside, then I know I'd have an under approximation because I'm going to be missing some of that blue area at that point, okay? So here's what we're going to do. We're going to keep the same subdivisions, right? So the 1/4, 1/2, 3/4, that doesn't change. But now I'm going to try to draw all of my rectangles so that they're under the curve. Well, that means that in this case, this second rectangle is actually going to be right here now. And the first rectangle has to be right here. Okay, so I know it looks weird, right? Because it has a height of 0 in this case, but that's the only way that I can get a rectangle, quote unquote, that's actually under the curve everywhere between 0 and 1/4. Okay, then I'm going to do the same thing at 1/2. I'm going to follow that up here. Then I'm going to make sure that my rectangle is completely under the curve. And then finally at 3/4, I'm going to go up here. And again, just make sure that that rectangle is completely under the curve. All right, so now I'm going to erase my work over here just so I've got some space to work. I want to find the areas of these rectangles now. Okay, so if I look at the first rectangle, quote unquote rectangle, how would you find the height of that rectangle? What value would we have to substitute in x? Okay, good. We're going to plug in the x value. What x value are we plugging in to find the height of that first rectangle now? And the first rectangle is the flat one. So 1/4 is going to give us the area of that rectangle between 1/4 and 1/2. I want to know the height of the one between 0 and 1/4. So what x value I plug in to get that 0, right? Okay, so I'm looking at this leftmost endpoint now, and I'm plugging in 0 because that's going to give us 0, right? And that's what we want. We want the height to be 0 there so that the entire rectangle is under that curve. Now, the rectangle between 1/4 and 1/2, I'm going to substitute what x value? That's going to be 1/4. Good. We've already done this, right? 1/4 squared should give us 1/16. Right, now my next rectangle, to find its height, we're going to plug in what? 1/2. Good. Again, we've done that calculation already. 1/2 squared should give us 1/4. And then finally, the last one, we're going to plug in what? 3/4. Good. And again, 3/4 squared should give us 9/16. Okay, so notice this time we're not using the 1 because we don't have any rectangles that have that height, right? So all of our rectangles this time, we're using those left endpoints for our rectangles. So starting from 0, then 1/4, 1/2, and 3/4, those are the 4 rectangles now. Now, what's the width of each of our rectangles? Still 1/4, right? So that hasn't changed. So we're still taking 1/4 as our width. We're going to add up all the heights. This time that's 0 plus 1/16 plus 1/4 plus 9/16. So again, at that point, we can just use our calculator. And decimal or fraction is fine here. So once you get that, let me know what you got. Good, 7/32. Or again, if you prefer the decimal, that's 0.21875. Okay, so either one of those answers is fine. And now again, I'll ask, is this an over approximation or an under approximation? This one's going to be under, right? Because this time we've actually got some blue area that we're missing, right? So all this stuff right here, we're not actually calculating. And so we're going to say this is actually an under approximation of our actual area. Now, the reason we do this is because now I know that my actual area is somewhere between the two values we got. So 0.21875, and then the other one was 0.46875. Which is a relatively low range, right? Okay, so we know it's somewhere between those two values. Eventually, we're going to learn how to find the exact value of that area, right? That's where we're headed. But for right now, we're just saying, all right, if I've got 4 rectangles, let's get an under approximation, an over approximation. We know our area is somewhere in between there now, okay? Again, the process here is always going to be find the width, then plug each of those x values in to find the heights. We sum up the heights, multiply by the width. That's going to give us our approximation. Any questions on that one now? All right. Now, for that same region that we just saw in example 1, we want to show that the sum of the areas of the upper approximating rectangles, meaning the right-hand endpoints, that was the first way we did it, approaches 1/3. Okay, so in other words, we're trying to say the limit as the number of rectangles approaches infinity of that region is going to be 1/3. right, so here's how we're going to do that. We're going to think of it exactly the same way that we just did, except now we need to think of taking a limit as that number of rectangles approaches infinity. So I'm going to start with my limit here. So limit as n approaches positive infinity. We know the two things that we need here are the width and we need the heights of all of our rectangles. Well, if n is approaching infinity, I'm going to have n rectangles, right? An undetermined number of rectangles. We're going to call it n. What would the width of our rectangles be then if we have n rectangles this time? Okay, so if we think about it, on the previous one, right, we had 4 rectangles, and each one of them was 1/4 wide. Now, I'm saying we have n rectangles, so what would the width of each of those rectangles have to be? All right, let's do this. So with 4 rectangles, the width was 1/4. What if there were 8 rectangles? What if I had 8 rectangles? What would the width be for this same picture? 1/8, right? What if I had 20 rectangles? Exactly, right? Okay, so it's 1 over the number of rectangles because that's what we're doing. We're taking an interval that's from 0 to 1, it's 1 wide to begin with, and we're dividing it into n pieces, right? So it's just going to be 1 over n is going to be our width now. Okay, so if we're looking for the width, it's going to be 1 over the number of rectangles. Any questions about that? Okay, so that means what I'm going to do is I'm going to put the 1 over n out front here because that's my width. And now I want to multiply it by the sum of all of our heights. Okay? Well, let's think about how we're going to find the heights of each of these rectangles. We're looking at the right-hand endpoints. Sorry. We know in this case the first one was at 1/4, the next one was at 1/2, the next one was at 3/4, right? So if our rectangles are only 1 over n wide instead, where is that first rectangle actually going to be? What would be the x value? So we're still starting from 0. The width is now 1 over n. So where is the first rectangle going to land? At 1 over n, right? So what we need to do is we need to plug that into our function. We're still using the x squared function. So this is going to be 1 over n squared. That's the height of that first rectangle. Plus, now we need to know where the next rectangle is going to land. Okay, so if each one of these is 1 over n, what would be the next x value that we're going to use then? We're thinking we've got our interval here from 0 to 1. We're putting the first one at 1 over n. The next one's going to be 2 over n, right? And then the next one would be 3 over n, 4 over n, and so on until eventually we get to n over n, which is the one down here, right? So this next one's just going to be 2 over n squared plus the next one's going to be 3 over n squared because, again, we're just adding 1 over n each time plus ... because there's an infinite number of these, right? I can't list them all out. But eventually, that last one is just going to be n over n squared. So again, process basically, other than the limit in this case, is the same, right? The width is 1 over n. The heights, we're finding those x values, we're plugging it in, so we're squaring each one, and then we're adding those heights together, right? So this piece, all of this stuff is exactly the same as what we just did. We just have an indefinite number of rectangles now. Any questions about that setup for this one? Okay. Now that we've got that, we need to try to calculate the limit as n approaches infinity for this thing over here. Well, the problem is there's an infinite number of things, right? We've got that dot, dot, dot in there. So we've got to think about a way that we could actually simplify this down so that we can actually calculate that limit, because our goal is to prove that that limit should be equal to 1 over 3 now. Okay, so again, I'm going to keep my limit. N approaches infinity. I'm going to keep my 1 over n out front here. And now I want to think about, is there anything that all of the terms inside here have in common? So basically, is there a common factor there that I might be able to pull out? So if you look at each of those terms, 1 over n squared, 2 over n squared, 3 over n squared, is there anything they all have in common? Okay, good. They all have the n, right? Where is the n? It's in the denominator, right? Okay, so basically we have a 1 over n in common for all of them. And then what are we doing to all of those 1 over n's? We're squaring them, right? So really what we end up having here is 1 over n squared as our common factor. Now we just got to figure out what's left over if we do that, right? If we factor out the 1 over n squared. What's going to be left in that first term, 1 over n all squared, if we factor out the 1 over n squared? Just the 1, but what are we doing to the 1 also? Everything in parentheses is being squared, right? So we also have a square on the 1. So we have 1 squared plus, what about the 2, right? Because that's what's left over here. What are we doing to the 2? Squaring it also. Same thing with the 3. So that's going to be 3 squared plus dot, 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 all the way up until we get to n squared. So again, the 1 over n is our width. Now we have this 1 over n squared as a common factor between all of our heights, so we can bring that out. And then all that's left over is 1 squared plus 2 squared plus 3 squared and so on until we get all the way to n squared. Any questions about what I did on that step? All right, now I'm going to go ahead and combine the 1 over n and the 1 over n squared here, because that's just going to give me 1 over n cubed. So I've got the limit as n approaches infinity, 1 over n to the third, right? Because I would square the n in the denominator there, multiply it by this other n in the denominator. It's going to give us 3 n's down there. Now, this thing right here, 1 squared plus 2 squared plus 3 squared and so on, it's an infinite sum, right? Because I have an infinite number of rectangles now. So I'm actually going to write this as a summation, right? And this is probably brand new. Maybe you've seen it somewhere along the way. We're going to use what's called sigma notation to represent a sum. Okay, so whenever you see that, it's talking like we're adding a bunch of things together now. Okay, now we just need to indicate where we're starting the sum and where we're ending the sum. And so we call this an I value. So our first value is going to be 1, right? Because that's where we're starting, is 1 squared. The last value we're squaring is n. Okay, so we're going from 1 to n for our sum. And then inside the summation, we just need to indicate what we're actually doing. We're squaring all of these values. So we're squaring the I values. So all of that infinite sum, 1 squared plus 2 squared plus 3 squared and so on, we can just simplify to this thing right here, the sum from 1 to n of I squared. Any questions about that? Now, the reason this is important is because now we actually have a formula for this thing right here. Okay? And on the test, I would always give you these formulas for the infinite sums. I'm not going to expect you to memorize them. Okay, but this right here has a very specific value in terms of n. So we've got our limit as n approaches infinity, 1 over n cubed still. But now this piece right here, that summation, is going to be n times n plus 1 times 2n plus 1 all over 6. And if you go on to take Calc 2, right, these are things that you're going to be expected to memorize eventually. So especially like I cubed and or I squared, I cubed, those specific ones, you're probably going to want to start memorizing those formulas if you're planning to go on to Calc 2 and Calc 3. Okay, so these will definitely come up again. But again, that summation is just equal to this thing in the brackets, and that's just a formula. Now, once I have everything in terms of n's, though, now I can actually start to evaluate this limit. So let's think about what I can do to simplify this first. I'm still taking my limit as n approaches infinity. So is there anything we could do to simplify this right off the bat that would make it a little easier to calculate? And I'll give you a hint. Always look for common factors in the numerator and denominator, because if you can cancel something out to simplify it first, it saves us some work in our multiplication. Okay. So is there anything that would cancel here? Yeah, right. We have an n in the numerator. We have an n cubed in the denominator. So one of those n's can cancel out. So in the numerator now, it's just 1 times this. So I'm going to cancel out the n. That's going to leave us with n plus 1 times 2n plus 1. And now down here, one of those n's cancels, and I have a 6. So we're going to have 6n squared. All right, now let's go ahead and multiply out the n plus 1 and the 2n plus 1. So if we FOIL that, sorry, I'm going to slide it over just so I've got more room to work. What are we going to get in the numerator if we FOIL that now? Good, right? So that's just going to be 2n squared plus 3n plus 1, still over 6n squared. All right, now, what would our next step be if we're taking a limit as n approaches infinity here? Okay, good. Look at your degree in the denominator and divide every single term by that. So we're going to divide everything here by n squared. So I'm going to create a new slide just so I don't have to squeeze all that down there. And I'll just copy what we just had. So again, we're looking at the limit as n approaches infinity. We had 2n squared plus 3n plus 1 all over 6n squared. And now we're going to divide all of our terms by the n squared. So we have limit n approaches infinity. We have 2n squared over n squared plus 3n over n squared plus 1 over n squared, and then our 6n squared over n squared. All right, so now we just need to go through, simplify each one of those. First term, 2n squared over n squared, that's just going to give us 2 because the n squares cancel. Next term, one of the n's cancels, so that's going to give us 3 over n. 1 over n squared we can't do anything with, so that stays the same. And down here, the n squares cancel, so that's just going to give us a 6. All right, so now let's evaluate this limit. What's the limit as n approaches infinity for 2? Just 2, right? It's a constant. What about the limit of 3 over n? It's going to be 0. 1 over n squared, also 0. And the limit of 6 is a constant, so it's going to be 6. If we simplify all that now, what do we get? 1/3, and that's exactly what we were trying to prove there. Okay, we wanted to show that the exact area of that region is 1/3, and that's what we did. Again, the way we did that was we said, let's let there be an infinite number of rectangles now so that each one of their widths is actually approaching 0, right? They're right on top of each other. And by doing that now, we get this nice smooth curve. And that's the exact area between 0 and 1 of x squared under that curve. And if you recall, back on example 1, we said that our exact area should be somewhere between 0.21875 and 0.46875. 1/3 would be 0.3 repeating. That's right there in between those two values. Okay. Any questions on anything that we did for this problem now? Okay, so this piece back here, right, all of this is a formula for this summation. So once we recognize this as just the sum of all the numbers between 1 and n of I squared, that thing right there is a formula. And like I said on the test, if I give you one like this, I would give you that formula. Okay, I would tell you that the sum from 1 to n of I squared is equal to that. And then you would know just to substitute that in place once you get it down to that. So the n cancels out because we have an n cubed down here, and we have an n up here. And so since we're multiplying these together, right, the n cubed would go in the denominator, the n's already in the numerator, so then I can just cancel out one of those n's, and that's how I get an n squared on the bottom, and that n on the top just cancels out. Okay, it's basically just saying like n over n cubed, same thing as 1 over n squared now. Okay. Any other questions there? Like I said, the process here is going to be the same for all these problems. The formulas we have to use are going to be different depending on the function that we're working with, right? We used I squared because the function was x squared. function was x cubed, we'd end up with a summation of I cubed instead, right? And then we'd have to know the formula for that one. But again, I'll give you that. Okay, but find your width, find your heights, set up that summation, plug in the formula, simplify your limit, and then that's going to give you your answer. And again, that answer represents the exact area under that curve now. All right, so the area A of a region S that lies under the graph of a continuous function, okay, it has to be continuous, is the limit of the sum of the area of approximating rectangles. Okay, so again, we started by approximating with 4 rectangles, then we said, all right, let's look and see what happens if we have an infinite number. That's exactly what we're doing here. Okay, so we're taking the limit as n approaches infinity for our region. That's the limit as n approaches infinity. This is a height, this is a height, this is a height, and then these are the widths, right? And delta x here just represents the change in x, right? So each one of our rectangles here has a width of delta x. And like I said, typically we just take that delta x and factor it out since it's a piece of all of them. That's going to help us to simplify that sum once we factor out that delta x. So if you just want to start with it on the outside, you can do that. All right, so now we want to let A be the area of a region that lies under the graph cosine x between 0 and some value b. Okay, but in this case, b is somewhere between 0 and pi over 2, right? So just to kind of give you an idea of what we're looking at, I'll just sketch this out. We know cosine starts at 1, and then pi over 2 is the first x-intercept. So we're basically just looking at a region that looks something like this now. Okay. Now, I'm going to skip part A. I don't want you to worry about that one. I actually want to look now at an estimate of the area where B is equal to pi over 2. So we're looking at that entire area from 0 to pi over 2. And we're going to use midpoints this time. And we're going to use 4 subintervals or 4 rectangles. All right, so let's think about what this is going to look like now. So again, sketch this out a little bit larger here. Starting up here at 1. Going out here to pi over 2. All right, so if I want to do 4 subintervals, okay, let's start by just figuring out what's the width of each one of those rectangles going to be. How are we going to find the width this time? All right, tell me this. What's the total width of the region that we're looking at? Pi over 2, right? So we're going from 0 to pi over 2. We want to divide that into 4 rectangles now. So if I divide that entire region into 4 rectangles, how wide would each one of those rectangles need to be? Perfect, right? Because all we're doing here, I'm going to call it delta x because that's how we're going to define it moving forward. We're just taking the pi over 2 minus 0 to get the width of our region, and we're dividing it into 4 subintervals. Pi over 2 divided by 4 should give us pi over 8, right? You could think of it as pi over 2 times 1/4 is another way to do it. Just multiply by the reciprocal there, and that would give us pi over 8. All right, so now we know if we divide this thing up, this is going to be pi over 8. What would be the next value here? Good, right? Because we'd have 2 pi over 8, which is the same thing as pi over 4. And then what would be the next value? 3 pi over 8. Perfect. All right, so those are the places where we would actually have our rectangles now. Now, here's where you have to be careful. On the first example, we did right-hand endpoints and we did left-hand endpoints to give ourselves an over approximation and an under approximation. This time, though, they're asking us to use midpoints because what that'll do is kind of average out the over and under approximation for us. So instead of using pi over 8, pi over 4, 3 pi over 8, and pi over 2 as the points that we want to use for our heights, we're actually going to create our rectangles now at these midpoints in between. So we need to know the x values halfway in between each one of those values, okay? Because that's what we're going to plug into our function to actually evaluate what those heights should be this time. Well, how would I find the point halfway between 0 and pi over 8 then? Okay, good, right? So we're just going from 0 to pi over 8. I want to cut it in half. So what's half of pi over 8? Pi over 16, right? So this is going to be, and here's the actual calculation. We're basically averaging the values. So it's pi over 8 plus 0, and then we're dividing by 2, right? But if we do that, that should give us pi over 16. So that's actually the x value that we want to use to calculate the first height. So then we're going to say f of pi over 16. Remember, our function here is cosine x. So this is going to give us the cosine of pi over 16. That's our first height. Now we need to do the same thing with each of these other x values, right? So if I want to know the value halfway between pi over 8 and pi over 4, again, I can just average those together. So we'll do pi over 8 plus pi over 4. Divide that by 2 to average them. What would that give us if we do that calculation now? It's going to be 3 pi over 16. Good. So we get 3 pi over 8 in the numerator divided by 2. It's going to be 3 pi over 16. Now, another way you could do this is we know the difference between each one of these midpoints should also be pi over 8. So you could just add pi over 8 to that first one that we found. Okay, that's another way to get each of these midpoints at that point. Okay, but then we need to plug that in to find our height. So we're going to have f of 3 pi over 16. That's just cosine of 3 pi over 16. Notice I'm not calculating these, right, because they're not going to be nice values. They're not on the unit circle. So eventually we'll just put it all in the calculator to get these values. All right, so now we need to know the next point. So I need to know the height over here now between pi over 4 and 3 pi over 8. How are we going to get that? Good. It's going to be 5 pi over 16. Again, either add them together, divide by 2, or just add another pi over 8 to 3 pi over 16. Either way, you're going to get 5 pi over 16. So again, let me create a new page just so I got plenty of space to work this out. Okay. So again, we're looking now between over 4 and 3 pi over 8. We can divide that by 2. And we said that should give us 5 pi over 16. And then we need to know the height there. So again, just plug that into our function. We have cosine of 5 pi over 16. All right, and then finally, we just need that last value that's between 3 pi over 8 and pi over 2. So if we average those values, what should we get there? Good, that's going to give us 7 pi over 16. And again, to find the height, we just plug that into our cosine function. So we get cosine of 7 pi over 16. All right, any questions about how we got the midpoints this time to calculate those heights? Again, this is a good way now to get a decent approximation that kind of averages out the over and under approximations. Okay, so that's why we like to use midpoints sometimes. All right, so now if I'm actually calculating the area, what's the width that we're going to use this time? Okay, so be careful, right? The first x value was at pi over 16, but how wide are the rectangles themselves? They're still pi over 8, right? Because the rectangle is actually going from here to here. It's just that part of it's in and part of it's out, right? Same thing with the next rectangle. It's actually going right here. It's just that part of it's inside, part of it's outside. Same thing with this next one. It's going from here to here. And then this last one is going to be right here. Okay. So you can kind of see better with those last two. You know, we're under approximating the left side and over approximating the right, but those over and under approximations end up canceling each other out a little bit. So you get a pretty decent approximation by using those midpoints. All right, so we're going to start here with pi over 8. That's our width. And now we're just going to add together all the heights, right? Well, that was just cosine of the first one was pi over 16 plus cosine of 3 pi over 16 plus cosine of 5 pi over 16 plus cosine of 7 pi over 16. Right. And then, like I said, at that point, I would just go to the calculator, put all that in there. Make sure you're in radian mode when you do it. Right. And then I would just get a decimal value for this one, right? Because, again, it's not going to be a fraction. It's not going to be anything nice. So go ahead and do that and let me know what you get. Okay. Yeah. So if we round this off, I think, does it come out to like 1.006 or something like that? We keep it decimal places. Okay. Yeah. So this right here, right now, I didn't tell you what to round to. Okay. But this would be an approximation now of that area under the curve from 0 to pi over 2 using our midpoints to calculate that area. Now, what I'll tell you, eventually we're going to do this problem again and find the exact area. The exact area here is going to be 1. Okay, so 1.006 is a very good approximation of the exact area between those two values now. And that's why we like to use midpoint sometimes, because a lot of times the over and under approximations cancel out, and then that'll give us a better approximation of what the actual area should be. Any questions on that one now? No, so you could just call it units squared if you really wanted to, but in this case, because we're just looking at a graph, right, we don't actually have centimeters or inches or feet or anything like that. So these are just numerical values. Yep. Any other questions there? All right, let's take our break here. So it's almost 11:02, so we'll say 11:07. We'll get started back up and finish up this section. All right. Example 4. So this is our last example in this section, and then we'll try to get into 4.2 today. So suppose the odometer on your car is that should be broken, and we want to estimate the distance driven over a 30-second time interval. We take the speedometer readings every 5 seconds and record them in the following table. Okay, so basically, we're saying when we first start out, our velocity is 17 miles per hour. After 5 seconds, we look, and it's 21 miles per hour. After 10 seconds, we look, it's 24 miles per hour, and so on. Now, to be able to do this, because our time is in seconds, we need to get some kind of velocity unit that also has seconds in it. So we need to convert our velocity to feet per second instead of miles per hour, okay, just so we can actually do these calculations. So if I want to go from miles per hour to feet per second, what would that conversion look like? I'm starting here with 17 miles per hour. If I want to convert that to feet per second, what would I need to do? All right, good. So there's 5,280 feet for every mile. So the first thing we can do is convert miles into feet. Now here's how I do all of my conversions. I know I want to cancel out miles, so they're going to go on the bottom. I want to end up with feet, so those are going to go up top. And I know there's 5,280 feet for every 1 mile. And then my miles are going to cancel. And so then I would have feet per hour at that point. Okay. I need feet per second now, so what else am I going to have to do? Okay, so 60 seconds in a what? So 60 seconds in an hour? Yeah, there's actually 3,600 seconds in 1 hour. If you don't know that, though, we could actually go from hours to minutes, then go from minutes to seconds, right? Okay, so let's do that. So I'm going to say, well, I need to cancel out hours. So I'm going to put hours up top. I know for every 1 hour, there's going to be 60 minutes. And now my hours can cancel out. And then I know there's 60 seconds for every 1 minute. So again, I need to cancel out minutes. I want to end up with seconds. So 1 minute is 60 seconds. Minutes cancel out. And now I have feet over seconds, and now I can do my calculation. Okay, so basically, we're multiplying 17 by 5,280, and then we're dividing by 3,600. Right, so if we do that, what does that give us? You can just round to the nearest whole number is fine. Good, 25, right? Because up top here, if you were to actually do just the calculation in the numerator and denominator, we'd have 89,760. We're dividing that by 3,600. And then that should round to 25. Again, this is feet per second. Right, so I'm going to go back to my table here. So right here, the conversion will give us 25 feet per second. And now all the other conversions are going to be the same, right? We're going to multiply the top by 5,280, and then we're going to divide by 3,600. So if we do that to 21, what's that going to give us? Good. If we round that, that should be 31 feet per second. Good. If we do 24 then, it's going to be 35. Good. What do we get for 29? Okay, good. If we round that, we'll round up to 43. Right, 32 then. $47, perfect. What do we get for 31? $45, good. And finally 28. $41, good. All right. Any questions about how we got those values by doing the conversion from miles per hour to feet per second? All right. Now, once we have our time in the same units, right? They're both in seconds at this point. If I want to know the distance I've traveled, what would I need to do now? So if you know time and you know velocity, how would you calculate distance? Okay. Tell me this. If you're going 60 miles per hour for 2 hours, how far have you traveled? 120 miles, right? And all you had to do to get that was multiply the time by the speed, right? Okay, so since our units of time are the same, they're both in seconds here. If I just multiply time and velocity, the seconds are going to cancel out, and that's going to give me feet, right? And that's my distance traveled. So that's all we want to do here is multiply those two things together. Now, to do that, though, we have to think about the fact that these are chopped up into intervals, right? How long is my first interval here? 5 seconds, right? So it goes from 0 to 5, but the total length of time from here to here is 5 seconds. How long is the next interval? It goes from 5 to 10. So what length of time is that? Still 5 seconds, right? So the length of time between here and here, also 5. What about my next interval? Still 5. And you should see in between each of these, always going to be a 5-second time interval. Now, how many 5-second time intervals do I have then? There's 6. How many velocities did we measure? Count them again. There's 7. Okay. So we have to be careful here. We have 7 different velocities, but we only actually measured in 5-second time intervals, and there's only 6 of those. So this goes back to that first example where we had both right-hand endpoints and we had left-hand endpoints. So we just have to decide which one we're going to do here, right? And we're actually going to do both, right? But let's figure out which one we want to do first. If we do the right-hand endpoints, what would be the first velocity that I would want to use here? Good, right? So at 5 seconds, we would use 31 feet per second, right? And we know the width of each one of these intervals now is 5, right? Because that's our time. It's 5 seconds for each one. So I'm going to go to my next slide here. I'm going to say my width is 5, and my first height, my first velocity, is going to be 31. And then I'm just going to add all of the heights or all of the velocities beyond that. So 35, 43, 47, 45, and 41. That would give me 6 time intervals if I use those values now. Okay. So 35, 43, 47, I think it was, 45. If I got one of these wrong, let me know. And 41. Okay. And if we do that calculation now, that should give us 1,210. What are the units going to be? Because we actually do have units on this one. Okay. So feet per second would be a velocity. We just calculated a what? Distance. So distance should just be feet, right? So that tells us if we use the right-hand endpoints for each of our 5-second time intervals, we traveled approximately 1,210 feet. Okay. Now, just like on example 1, we had an over approximation and an under approximation, we can also use the left-hand endpoints now to give ourselves a range of values that our distance could be. So I'm going to do the same thing. 5 is still the width of my rectangles, but this time we're going to start with what value instead for our height? The 25, right? So if we're using left endpoints, 25, and we're going to go up to which value? What's the last that we're going to use? So we're going up to the 25-second time interval, which means we're going to 45 as our velocity, right? So we're going to ignore the 41 this time because we only need 6, right? So it's those first 6 that we're looking at this time. We're going to have 25, 31, 35, 43, 47, and 45. And if we do that now, what should that give us? Good. So 1,130 feet. All right, so again, what that gives us now is a range of values for the actual distance. So we know our distance traveled should be somewhere between 1,130 feet and 1,210 feet. Now, that's pretty much the only way to do this problem in particular, just because we're given a table of values. We don't have a function that we can actually plug into. The only other option maybe would be to like average the velocities here, right, and get 6 averages and then use those as your heights instead. That would kind of give you the over-under approximation canceling out, but you would probably get something very similar. You could also just average our final answers here, right, and say, well, it's probably about halfway in between those two values. That will be another way to get a better approximation of the actual distance that you traveled. But again, just keep in mind here, velocity times time will give you distance. We're trying to figure out how far. The main thing, though, is because you've got 7 different velocities, we only need to use 6 of them because there are only 6 time intervals that we care about. Okay, so don't use all 7 in one calculation. Any questions on that one now? All right. Move on to 4.2 now. All right, so 4.2, the definite integral. So this is where we're going to actually define what an integral is, how it's related to those limits that we just looked at in the previous section. And then, like I said, once we get into 4.3, then we'll start to look at shortcuts for actually calculating these integrals. All right, so definite integral. If f is a function defined for some values between a and b, those are your x values, we divide the interval from a to b into n subintervals. Okay, so our delta x now, we talked about this in the previous section, we're going to take the two endpoints and subtract them to get the total width, and then we're going to divide by the number of rectangles that we want to create. And if they give you a set number of rectangles, then you actually plug that in for n. If it's an infinite number of rectangles, we just leave n in the denominator. All right, so we're going to let x sub 0 be equal to a, right? That's our leftmost endpoint. X sub n is going to be b, that's our rightmost endpoint. And then we have all these other x's in between, right? Those are going to be the endpoints of our subintervals. Now, this right here, the x sub 1 star, x sub 2 star, and so on, we call those sample points. Don't stress too much about that, because what's going to eventually happen, once we take the limit as n approaches infinity, those aren't going to matter, okay? Because our width is going to be so negligible, right? It's going to be so small that we don't really need to worry about where that x sub 1 star actually falls within the interval or anything like that, okay? So the main thing to get here is how to find the delta x. And then down here now, the definite integral from a to b of our function dx, right? So that's what we call this, is the integral from a to b of f of x dx, is the limit as n approaches infinity of the summation from 1 to n of our function times delta x. That's exactly what we did in example 2, right? We took the limit as n approaches infinity of the sum of all of our heights times the delta x, which is the width of our rectangle. We simplified that, and that gave us the exact area under our curve. So really, when we're calculating an integral now from a to b, we're asking ourselves for that function, what's the exact area under that curve on that interval from a to b? Okay. So this is our limit definition for an integral now, how we're actually going to calculate these integrals. And then down here, just if you ever see the word integrable, right, that just means that you can actually calculate the integral. Any questions about any of the notation on this slide right now? Okay. All right, and so you can see here, basically what's happening again is we're taking these rectangles, we're trying to create an infinite number of them, and when we do that, that delta x just becomes really, really, really small, right? And we've got all these rectangles right on top of each other. It smooths out our curve, and it gives us the exact area under that curve now. Right, now, the symbol, right, and so that's our integral symbol, is called the integral sign. In the notation, integral from a to b of f of x dx, f of x is called the integrand. That's the thing we're taking the integral of. A and b are our limits of integration. A is the lower limit, b is the upper limit. Okay, so a is always going to be on the bottom, that's your lower limit. B would be on the top, that's your upper limit. And the dx here just indicates that we're taking our integral with respect to x. Okay, so it just tells you what your independent variable is. A lot of people see it and they go, oh, well, that's just like delta x. It's not, okay? So be careful there. They're not the same thing. The dx just indicates what your independent variable is. And then we call this integration whenever you're calculating an integral. The other thing to note here is that because we're calculating an area, you are going to get a numerical answer for all of your definite integrals. Okay, so anytime you're finding a definite integral, it should be a numerical answer. And the last piece of this just says the definite integral can be interpreted as a net area or a difference in areas. I'm going to show you on the next slide what we mean by that. But basically, we're taking the area that's above the x-axis and we're subtracting any area that might be below the x-axis. Okay, so anything above we consider positive, anything below we consider negative. And so you can see in this case now, we would take all these blue shaded regions and think of those as positive areas. Anything below here would be considered a negative area. And so then we would put all those together. In this case, because it's symmetrical, these would actually just cancel out. So the net area of that region would be 0. Again, we'll spend more time on that, right, thinking about positive and negative values. But just keep in mind, anytime it is possible to get negative answers for these definite integrals. And if that's the case, that just means that more of your area is below the x-axis than is above. Okay. All right, I know there's a lot of notes here up front. Okay, so if f is continuous on the interval from a to b, or if f has only a finite number of jump discontinuities, meaning we can just count up like all the places where it jumps, then it's going to be integrable on that interval, and the definite integral exists. Okay, so as long as it's continuous, that's going to be most of the functions we look at. Or if you can actually see and count all the jump discontinuities, you could still calculate an integral on that interval. And again, here's all of our formulas. Again, this stuff down here is the main thing you need to focus on, because this is what we're going to be doing. Okay, so if you're looking for an integral from a to b of f of x dx, we're taking the limit as n approaches infinity of the summation from 1 to n of f of x sub I times delta x. F of x sub I, just know it's the same as f of x. We're just plugging in the x sub I value instead, and delta x is still our width. Okay, and then we're going to use delta x equals b minus a over n to calculate the width of our rectangles. And then the x sub I piece is going to be the starting value of your interval, a, plus I times the width of our rectangle. Okay, because that's going to tell us then where are each of those rectangles going to land. Okay. Again, I'll write out these formulas at least the first few times that we use them, just so we get comfortable, because you will need to memorize these, because on the test you'll need to know how to calculate the width of a rectangle and how to find each of those subintervals. All right, so first thing we want to do here, they give us a limit definition. We want to rewrite it as an integral. Okay, so this time they're telling us our intervals from 0 to pi. We're taking the limit as n approaches infinity of this summation up here, and we want to rewrite this as an integral. Okay, so based off everything that we just saw, what's something that we could put in our integral here? So just to remind you, what we're trying to do now is write it in this form. Integral from a to b of f of x dx. Because we know that limit definition up there should convert to this. All right, good. The b and a values are from 0 to pi, right? That's going to give us our lower and upper limits of integration. 0 is the a value, so that goes down here as our lower limit. Pi is the b value, so that's our upper limit of integration. Perfect. Okay, so we got that part. What's our f of x going to be this time? Okay, so it's not going to be 1, right? Because remember, inside here now, this piece is f of x sub I. Okay, that's part of our limit definition. Well, if that's f of x sub I, what would just f of x look like? It's exactly the same thing without the i's, right? So it's going to be x cubed plus x times the sine of x. So there's our f of x. And then what's the only other thing we need now? Dx, right? Because we have to tell it what our independent variable is. So we say dx now. That's it. Okay. So if you're just trying to rewrite that limit definition as an integral, make sure you recognize, right, this is our a and b values for our interval. So that's going to go from 0 to pi. And then our f of x sub I, just drop the i's. That gives us our function. And then we just have to tell it that we're taking it with respect to x. So that's where the dx comes from. Any questions on that one? All right. So now we want to evaluate a Riemann sum. And by Riemann sum, we're just talking about that summation notation we just looked at. For f of x equals x cubed minus 6x, by taking the sample points to be right endpoints, our interval goes from 0 to 3, and we need 6 rectangles, 6 subintervals this time. All right, now I'm just going to move this down so I can work this out, and then we'll probably go to the next slide, do the second part of this one. All right, so if we're taking a look at part A here, what's the first thing we're going to need to know to be able to get this approximation, right? Because for the Riemann sum up top, we're just looking at an approximation using 6 rectangles. So what would I do first? Okay, so our A and B values, right, are 0 and 3. So what are we going to do with those? And I'll tell you, this is pretty much just like example 1 from the previous section in terms of what we're doing. We just have a different number of rectangles now. What are we going to have to do first? So what's one thing that we need to know to be able to calculate the approximate area under this curve? Okay, well, yeah, so we're given that n equals 6, right? So think about this. On the very first example we did, we were going from 0 to 1, and we wanted 4 rectangles. Well, this time, we're going from 0 to 3, and we need how many rectangles? We need 6, right? Okay, so I know in this case, I'm going to divide this first one in half, and then I'm going to put 2 in here, 2 in here. Sorry, those aren't exactly even. See if I can make that a little better. So 1, 2, 3, 4, 5, 6. Okay. I need to know the widths of each one of those rectangles now. How am I going to find the width of my rectangles? Exactly, right? The total width is 3. I'm dividing it into 6 equal pieces, so it's just going to be 3 divided by 6. That's our delta x, right? So delta x is 3 minus 0, that's b minus a, over n, which in this case is 6. Well, what's 3 over 6 going to give us? 1/2. Perfect. Okay. So whenever we're calculating delta x, we're just calculating the width of our rectangle. And again, to do that, it's the b value minus the a value to get the total width of the region. And then we're dividing it by the number of rectangles. In this case, we're given that there are 6 rectangles. Any questions about that step? All right, now what's the next thing we're going to need to find? The lengths, right? Okay, so we know the widths now. Let's find the lengths. Well, to do that, remember, we just need to know what each of these values are so we can substitute them into our function. Well, what's our first value going to be at that tick mark right there? 1/2, right? So we know our first value, and this is going to be what we call x sub 1 is going to be 1/2. Now, to calculate that, remember we have our formula for our x sub i's. I can go back and show you right here. I'm going to use this formula just because it's going to be useful for us down the road when we have an indefinite number of intervals. So x sub 1, in this case, is going to be the a value plus 1 times delta x. We're going to start with our a value, which in this case is 0, plus 1 times delta x. So where is that first x value going to be? It's going to be at 1/2, right? So we know that this one right here is 1/2. Where is the next x value going to be? It should be at 1, right? Because it should be another half. So we're just going to do 0 plus the I value, which again is this value down here. So 2 times our width. 0 plus 2 times 1/2 tells us the next one is going to be at 1. Okay. Where is our x sub 3 going to be? Hey, be careful. We only want to go up 1/2 from there, right? So it should be what? 1.5 or 3/2, right? Because again, we're just doing 3 times 1/2, which is 3/2 or 1.5. Now we should have 6 of these, right? So let's look for x sub 4. Again, our a value is still 0. We're using 4 this time, times 1/2 is our width. So what is that value going to be? That one's going to be at 2. X sub 5, 0 plus 5 times 1/2 is going to give us what? 5/2 or 2.5. And then finally, x sub 6 is our last one. 6 times 1/2 is going to be what? 3. Good. And if we're doing right endpoints, okay, that rightmost endpoint should be your rightmost endpoint of the actual interval, right? So 3 should match up with the actual endpoint. So now we have 3/2, we have 2, we have 5/2, and then we have 3. All right, so now we're trying to calculate the sum here. So sum from 1 to, in this case, our n value is 6. So we're just going from 1 to 6 of our function times delta x. And that's what we're calculating. In other words, though, we're just taking the delta x value and we're multiplying it by the sum of all of our heights. Okay, so the next thing we need to calculate are the actual heights for each of these x values. How are we going to calculate those heights? Yeah, just plug it into the equation, right? We're given the function, we know the x values, we're just going to plug them in now. So we're going to have f of 1/2. If we substitute 1/2 into our function, what are we going to get? And decimal's good here. So if we just plug in half, okay, negative 2.875, good. All right, we're going to do the same thing with the other x values. So f of 1, what should that give us? That's going to be negative 5, good. F of 3/2 or f of 1.5. Good, negative 5.625. We have f of 2. Negative 4, good. F of 5/2 or f of 2.5. Good, 0.625. And then finally, f of 3 is perfect. All right, so there's all of our heights, right? And so if you go back and look at our formula, we're taking the delta x, which is the width, and then we're multiplying it by the sum of all of those heights. So this just becomes 1/2 times, and then I'm going to add up all of these values here. Negative 2.875 minus 5 minus 5.625 minus 4 plus 0.625 plus 9. Again, exactly the same thing we did back on example 1, except now we just have a formula that we're trying to use to actually do the calculation. Again, it's find those x values, find the widths of your rectangles, plug in the x values to find your heights, add up all the heights, multiply by the width. That's all we're still doing. Now, if we do that calculation there, what does that give us? Perfect. Negative 3.9375. All right, so again, that is an approximation of our area under the curve x cubed minus 6x on the interval from 0 to 3. Now, based off of that area that we got, that answer, what's something that we know about this area now? Okay, so is our answer positive? It's negative. If we get a negative value for our area, what does that tell us? Okay, more of our area has to be under the x-axis than above the x-axis, right? And you can see just in our height approximations over here, these first four heights are all negative values, right? So those are all y values that are below, and only the last two are above. So more of our area now is going to be below the x-axis than above the x-axis. That's what it means to have a negative answer, okay? So it's saying that from, all right, let me show you the graph, okay, because I think that might help clear it up a little bit more. Let me switch over to Desmos and we'll just focus on our graph here on that interval from 0 to 3. So we've got x cubed minus 6x. Again, I'm just graphing from 0 less than or equal to x less than or equal to 3. Amount. Okay, so there's what we've got. When I'm calculating this area now, right, I'm only looking from 0 up to 3, right? But notice here, I've got a lot of area between 0 and 2.449 that's negative, right? That's below the x-axis. And then I've only got this little skinny section over here that's above, right? So that area in the positive is not going to be nearly as much as that area that's below. And since I have more negative area than positive area, I end up with a net area that is negative. Okay, so we're not saying the entire thing is below. We're just saying that more of it is below than above. That's all. Any questions there now? All right, so we'll stop there for today. We'll come back and pick up with B tomorrow. Again, I think the homework's probably going to get pushed back to at least Friday. For right now, definitely focus on the test. That's the most important thing. Make sure you get that done by midnight tomorrow night. And then the homework on 3.7 and 3.9, if you haven't finished that one yet, just make sure you get that done by midnight tonight, okay? Again, once we get to the shortcuts in 4.3, all these questions will become a little bit easier and faster. So even if you hold off and wait until Thursday to start those, I think you'll be okay. All right. Let me know if you've got any questions though, especially before you start your test. If you have any questions, let me know. I do have student hours tomorrow morning from 9 to 10. So if you want to drop in and ask me anything before you take your test, feel free to do that. Otherwise, have a great afternoon, and I will see you all tomorrow.